Welcome. Today is Wednesday, June 24th, 2020, and this is the NHERI webinar series. For more information about NHERI, look at the DesignSafe website, which is designsafe-ci.org, where you can find links to the SimCenter and the NHERI Learning Center for other upcoming webinars. Today's webinar is hosted by the Natural Hazards Engineering Research Infrastructures Computational Modeling and Simulation Center and DesignSafe. This webinar is supported by the National Science Foundation under awards 1612843 and 1520817. Any statements in this webinar are those of the presenter and do not necessarily represent the views of the National Science Foundation. Today, we're joined by Professor Catherine Gourley. She's an assistant professor of civil and environmental engineering at Stanford University. Her research activities focus on the development of predictive computational fluid dynamics simulations to support the design of sustainable buildings and cities. The title of her presentation is Predicting the Wind Pressure Coefficient Distribution on a High-Rise Building Using Computational Fluid Dynamics. Thank you, Professor Gourley, for being here, and I invite you to present.
Okay, thank you very much for the introduction. So before diving into the research, I always like to acknowledge that anything that I present is really the result of a collaborative effort by everyone in my lab. So here you see my graduate students, postdoc, and also former lab members. And for this talk specifically, all of the simulations that you will see have been done by Giacomo Lamberti. And what I'll present is a significant portion of his PhD research, which he defended about 3 weeks ago. I also want to take a few minutes to acknowledge our collaborators from the Politecnico di Milano. They have done the experimental data that we used for validation. They have very generously shared all of that data with us, and this work would not have been possible without that. I also want to thank our collaborators at the Florida International University Wall of Wind. And we performed some repeat experiments of the experiment in Milan there. And while I won't be showing these in today's webinar, they have really helped us understand the sensitivities of this data. Funding for the research came from an NSF award and my NSF Career Award. And then we run all our computational simulations on Exceed resources, which is also supported by NSF. So the motivation for this work is that we see an increasing urbanization. And because of that, we also see an increasing number of high-rise buildings. These high-rise buildings are often covered with cladding panels. And these panels can experience peak pressure loads during extreme wind events that can be catastrophic. In the pictures below here, you see a couple of examples of damage due to hurricanes and then a tornado as well. So when we try to understand wind loading on buildings, there are different methods that you can use. Currently in engineering, you can use standards or codes where you compute design pressures and loads using empirical expressions. The advantage of that is that these are very straightforward calculations to do. The disadvantage is that they will have limited accuracy because you might, for example, have interference effects with surrounding buildings, or you might be looking at complex building shapes for which the empirical data was not necessarily obtained. So the solution when wind loading is really a critical consideration in design is to do wind tunnel tests. And what you do in wind tunnel tests is you're going to record time series of pressures or forces on a scaled model in a wind tunnel. The advantage of this is that it's the established method for engineering design. We know how to do this and it's been done like that for decades. A challenge though, when you really look at the design of cladding is that you have a limitation in the number of measurement locations that you can put on a building and the resolution that you can achieve. Standard wind tunnel tests will sometimes only have one pressure measurement on the area that would be covered by a panel. And making the decision on what the average wind load on the panel will be based on just this one single measurement can lead to both over and under dimensioning of your system. And this is where CFD could actually provide a valuable alternative. The advantage of CFD is that you would get a complete three-dimensional solution for the flow field. So your number of pressure taps is basically equal to the number of cells on the building facade. So now you can go decide, I know the size of my cladding panels, how many cells do I want to put on a cladding panel to calculate a good average load. The disadvantage is that in CFD, you always have a trade-off between accuracy and cost. And the main choice to be made there is really how are you going to deal with turbulence. So either you do simulations that will resolve larger scales of turbulence, those are large eddy simulations. They will be relatively accurate, but more expensive. When you do Reynolds average Navier-Stokes simulations, you only solve for the mean flow, so you need to model all of the turbulence. These are much faster, but they won't be as accurate. In addition, it can be challenging to create a representative turbulent wind field in these simulations, and that particularly applies to large eddy simulations. So the objective of our work has been to enable the calculation of the pressure coefficient distribution on buildings using computational fluid dynamics. And we have focused on a high-rise building here, and our goal is to validate our results against available wind tunnel measurements. So this is a brief overview of the things I'll go over in this talk. First, I will introduce the test case and our quantities of interest in more detail. Then I'll give you a brief overview of the different steps, the different things that you need to think about when you set up a CFD simulation. And then we'll go to how we generate a turbulent wind field in a large eddy simulation. I'll discuss how we set up the simulations and then how we do an optimization to actually get the wind field that we're looking for. Then we'll apply this to the simulations of the high-rise building. So I'll again show you how we set up the simulation. And I'll discuss what the sensitivity is of our pressure coefficients to this inflow uncertainty. And I'll also briefly touch on the effect of the subgrid model for turbulence. And then depending on how long I take to do this, I might spend a little bit of time talking about Reynolds average Navier-Stokes simulations as well before wrapping up with conclusions and analysis. Okay, so let's start by looking at our test case and the quantities of interest. So we're looking at this high resolution experiment on a high-rise building, and all of the details on this experiment can be found in Luca Amerio's PhD thesis. We also have a paper that is in press comparing the measurements in Milan and the Wall of Wind. And then both of these data sets, the one from Milan and the one from the Wall of Wind, are available online. So if you're interested in looking at this test case and using it for validation of simulations, these data sets are freely available. So the case that we're looking at here is a 1:50 scale model of a rectangular plan building. It's 2 meters high in the wind tunnel. It's 1 meter long and 30 centimeters wide at model scale. It's tested in a closed loop wind tunnel of the Politecnico di Milano. And in this wind tunnel, they generate an atmospheric boundary layer, so a turbulent wind field, using a combination of spires upstream and then roughness elements further downstream. And then you have the turntable where the building is located in this picture. But what they did first in this experiment is to really carefully characterize what the atmospheric boundary layer flow is that you get using this setup. And that's what you see in this slide. So they measured 5 profiles at different span-wise locations here on that turntable and at 52 vertical locations. The measurements were done with 3-dimensional hot wires, and we have 20-second time series with a sampling frequency of 2000 Hertz. So for each of these span-wise locations, we can now go and calculate statistics, right? And what you see on the right here is the mean velocity profile, which follows a logarithmic law. And we both show the mean of the 5 span-wise locations, but also the variation that you see over these different locations. And the characterization of that variation was actually extremely useful when we did our simulations, because we could go and look at what is the sensitivity of our simulations to that uncertainty that we see in the wind tunnel. The pressure measurements on the building. So you see a side view here of the building. We're going to focus on the case with a wind angle of 0 degrees. And they have these, the focus on the critical locations near the corners and the edges. That's where you expect these high suction peaks to occur in the flow. We have 224 pressure taps on each of these tiles, and that results in a minimum tap spacing of about 3.4 millimeters, so extremely high resolution. And there are 300-second time series with a sampling frequency of 500 Hertz here. In this presentation, we'll combine the data that was obtained at 0 and at 180 degrees because of symmetry that will allow us to look at the full pressure coefficient distribution on the top of the building, and then we'll have one tile upstream and one tile downstream as well. These are results from an Elias simulation just to give you a sense of what flow topology we're looking at. So the colored contours here show you the streamwise velocity magnitude. And what you see is that you have this incoming boundary layer with a logarithmic profile, so lower velocity magnitudes near the ground than up high. That impacts the building, the flow goes up and down and to the sides of the building. So that results in these unsteady separation regions, both on the building roof and on the building sides. And we also have that unsteady wake behind. The black and white contour here is the pressure coefficient, so the non-dimensionalized pressure on the building facade. And you see that where you have that unsteady separation, you get these higher suction values that could result in failure of the cladding system. What this video shows you is again these contours of the pressure coefficient on the left. And then on the right here, you see isol surfaces of Q criteria. And these are representative of where we see turbulent vortices in the flow. And the thing that is very interesting when you look at this type of three-dimensional visualization is that there is a clear correlation between where we see these high negative pressures, and I'll pause the video here to clarify that. So we see these high negative pressures often starting from the corners of the building, both the top and the bottom corner. And you get these vortical structures that then move downstream. And you see here that the location of these vortices really corresponds to where we see these high negative pressure peaks. So we're really interested in understanding what the time statistics of these pressure coefficients on the building facade are, because these are what will determine the wind loads on the building. So when we look at a turbulent signal of a pressure coefficient, you would see something like this, right? So you have time on the x-axis and then Cp on the y-axis. And we're interested both in looking at the mean pressure coefficient, at the root mean square of this signal, but also at the peak pressure coefficient. So what are really the peak loads that you will see? Because we have these point-wise measurements, we can look at local peak pressures, but what is really of interest for engineering design is the peak pressure load on an entire panel. So you want to average over the panel first and then calculate the peak load. So these will be our 4 quantities of interest that we'll be looking at. And I'll first show you what these look like for the wind tunnel experiment. And these are plots that will come back over and over when we look at validation as well. Okay, so we have our pressure taps on the building here, and then you see the mean pressure coefficient that you get from the experiment. And whenever you see polymi, that stands for Politecnico di Milano, so that's the experimental data. So you see a mean pressure coefficient that has a suction here upstream because of the separation, and then the flow reattaches and you get pressure coefficients that are less negative. When you look at the root mean square, you see that you get the highest value for the root mean square more in the center of the building. And that is where the flow will alternate between being separated and then being reattached. So that's where you get the largest variations in the pressure coefficient. Then to get to the peak pressure coefficients, we don't just look at the time series and extract the most negative peak. There is actually a statistical process to determine. And we do that using the Cook and Main method. So you look at this time series of Cp, and for a peak coefficient, that is the value in one pressure tap. For the design pressure coefficient, that is the value averaged over all the pressure taps on a tile. You divide this time series in a number of windows, and in each window, you extract the most negative peak. And once you have done that, you fit a Gumbel distribution to all of these peaks so that you can find the pressure coefficient relative to a specific probability of exceedance. And in our case, we'll look at a 22% probability of exceedance. So what these look like is the following. So first I'll show you the local peak pressure coefficient. So this is the peak pressure coefficient at each of the pressure taps. And you see that you get these highest values inside of the separation bubble. Then when we look at the design pressure coefficient on the cladding panel, so we're looking here at the panel near the top corner. And then we look at different panel sizes. You see that you basically, this CP design becomes less negative as you look at bigger panel sizes, because you're starting to filter out these local negative peaks. And this is actually something that is important when you think about doing simulations, because getting these local peaks exactly right will be very difficult. That would require resolving all of the turbulence. But getting these design pressure coefficient right becomes a little easier, because you're actually averaging over an area. Okay, so in the next part here, I want to go over the steps in setting up a CFD simulation. And the idea here is really to highlight what the things are that you have to think about when you set up a CFD simulation, such that you're following the best practice. And the first step is always to define your quantities of interest. And we've done that here, right? We said we're interested in the statistics of a turbulent pressure coefficient. When you know what you're really interested in, you can go and select your turbulence modeling approach. And this is probably the most fundamental choice you're going to make. So let's look at that in a little bit more detail. Okay, so turbulence is one of the unresolved problems of classical physics. It's characterized by unsteady aperiodic motions with random three-dimensional spatial variations. There's a strong dependence on the initial conditions. And in a turbulent flow, you see a wide range of scales that we call turbulent eddies. So what we often do in a turbulent flow is we look at an energy spectrum. So we look at what is the energy content at different frequencies or wavelengths in the flow. And what you see in turbulence is that you have larger scales where you have production of turbulence kinetic energy. Then you have an inertial subrange where that energy is moved from the larger scales down to the smaller scales where you then have dissipation. If you want to numerically solve the turbulent flow equations fully, then your simulations have to be three-dimensional, they have to be time accurate, and they have to resolve all of these scales that you see in the flow, which requires extremely fine grids. So if you look at the different ways of solving a turbulent flow, it basically reflects how much of the turbulence you resolve. A direct numerical simulation will resolve all of this turbulence, but that is not affordable for the type of simulations that we're looking at. Our Reynolds numbers are too high and our geometries are too complex. So the next best thing that we can do is we can do a large eddy simulation. And in a large eddy simulation, we're going to be resolving these larger energy containing scales of turbulence, and we're only modeling what happens at the subgrid scale. So these simulations can still be very accurate, and they are actually feasible for complex engineering flows. Then the next step that you could do is do a Reynolds average Navier-Stokes simulations. And if you do this steady Reynolds average Navier-Stokes simulation, you only solve for the mean flow, and you would be modeling all of the turbulence. And you can imagine that coming up with a model that represents all of these scales and the effects of these scales on the mean flow is much more difficult than this, right? We've been trying to develop good turbulence models for decades, but still for bluff body flows, like what we're looking at in wind engineering, these models will not be very accurate. They are, however, very quick, right? So you can get a solution in a matter of hours, while we'll see here, we're talking more about weeks. So I'll be mainly focusing on large eddy simulations because it's generally accepted that for wind loading, you want to be resolving these turbulent scales of motions. If I have time, I'll touch a little bit on the run simulations at the very end. Okay, so you select your turbulence modeling approach, and then after that, you have three steps that are basically about setting up your model, your mesh, and how you're gonna solve your equation. So you need to define your geometry in your computational domain, which means you have to think about the level of detail in your model. For example, if your building has balconies, will you be resolving those in the geometry? You need to think about the size of your domain and the position of your boundaries. You don't want any unintended effects of your boundary conditions on your flow solution. Then you have to generate your computational mesh. So you discretize your computational domain. Here, mesh quality and resolution are very important because you want to be able to resolve all of the important features in your flow. Then checking grid dependency is something that is essential. We will never do a simulation with just one grid resolution. You will always check what happens when you look at different resolutions. Then selecting discretization schemes and solution methods, you always want to use at least second order schemes, and it's very important to check convergence of your solution. So I'm not going into a lot of detail here because there are best practice guidelines available for all of these. So if you're setting up CFD simulations, it's a really good idea to check on these best practice guidelines. Two of these focus on run simulations, but there is one that goes more into LES. And the concerns that you have in run simulations, for example, the geometry and the boundary conditions are also very similar to those in LES. Okay, the other thing that you have to do is you have your domain and you know where your boundaries are, but now you also have to define your boundary conditions. There is some guideline on that in best practice guidelines, especially for runs. And here I'll discuss much more what we will do for LES in our sections on the actual simulations. Then setting up post-processing, when you do LES, that actually requires very careful consideration because you cannot afford saving your entire flow solution at every single time step of the simulation. So you need to think in advance about where you want to save time series, what kind of mean flow solutions you want to save as well. And then validation is the other thing that I'll address in detail as we move on. So the boundary conditions are really very important. And I mentioned already in the beginning that especially the inflow boundary conditions in LES can be challenging. So I want to spend a bit of time talking about how we do this in a large eddy simulation. And since we're trying to validate against a wind tunnel boundary layer, our focus here will really be on reproducing the boundary layer that we see in the wind tunnel. And this has been published in this reference here. So if you want more details, you can go look there as well. Okay, so the setup of this inflow calibration looks as follows. So in this picture on the right here, you see what our domain looks like with the high-rise building in it. So we have a relatively long domain. Our high-rise building is about 5 meters from the inlet of our computational domain. Now, what we want to achieve is that our turbulence statistics at the building location here will actually be the statistics that we see in the wind tunnel. So what we do here is we specify a slightly smaller domain to make sure that these simulations will be affordable. And we ensure that whatever we specify at the inflow is going to give us the turbulence statistics that we want 5 meters further downstream. So the size of this domain is 10 meters long, 4 meters high, and 3 meters wide, and it's discretized with 5 million cells. Our first cell height here is 6.25 millimeters, and that gives us a Y plus of around 300 on the ground wall. So that's a non-dimensional wall unit that kind of tells us how much of the near wall turbulence we will be resolving. And in this case, we're not resolving it because we would need a Y plus of 1 to do that. So that implies that we'll need some sort of wall function, which I'll talk about as well. We set up this simulation with the most simple subgrid model because that was kind of the starting point. We wanted to see with the most simple model what kind of results we could obtain. Then for the boundary conditions, so in an LES, you always want to use periodic boundary conditions on the side because that will actually avoid that you are damping the turbulence on these side boundaries. We put a no slip condition on top. In the wind tunnel, there is a wall there, but we do not want to have to resolve that boundary layer because it's not affecting our quantities of interest. So we put that a no slip boundary condition there. And then I'll talk more about the inflow and the rough wall function on the next slide. In terms of the solver, so we use OpenFOAM with a piezo foam solver. And this is also, OpenFOAM is also the solver that is being used in all of the SimCenter tools. We use second order discretization schemes, a second order implicit time stepping schemes with a time step of 0.02 seconds. And that gives us a CFL number of less than 0.2. Then in a large eddy simulation, it's always important to let the turbulence and the flow develops to something that is a quasi-steady state before you start actually taking values for statistical averaging. So our burn-in period was 60 seconds, and then our statistical averaging was done over 160 seconds. These simulations took 5,000 CPU hours on 32 processors, which is about a week on Stampede 2. These are really representative of what you would get if you use the SimCenter tools, because they also use the Stampede2 cluster. Okay, so let's look a little bit more at what we need if we want our flow to be representative of the atmospheric boundary layer in the Windtunnel. So in terms of the mean velocity profile, we want to have something that follows a log-law fit. And you see that again here from the Windtunnel data. So you have a friction velocity here divided by the von Karman constant, and then the log of the height above the ground, and then the roughness length Z0. Now, in order to sustain that mean velocity profile, you actually have to make sure that your boundary condition on the floor of your domain, or the floor of your wind tunnel, if you will, supports this. And what you would see in standard CFD codes, and people have looked at that a lot for Reynolds average Navier-Stokes simulations, and you basically need to do just the same for a large-eddy simulation. So if you're not careful and you impose a log-law profile like this one at the inflow of your boundary, of your computational domain, and you just solve the simulation with a standard wall function on the ground, what you would see is that this profile will evolve. And by the time that that profile reaches your building here, it might look very different from what it actually is in the wind tunnel. And that would obviously affect your validation effort. Right? So what you want to do is you want to ensure that the wall function that you specify on the ground corresponds to that log-law profile here, and that it supports that profile. So when you do that, you will see that you do not have any unintended streamwise gradients of your mean flow. So that is a solution for the mean velocity profile, but we still have the challenge that we also want to represent the turbulence content correctly. Right? So this is the profile of turbulence kinetic energy that we see in the wind tunnel. And what we want to have in our simulation is that at the location of the building, our statistics match this type of profile. So how can you do that? And I'll be talking here mostly about Reynolds stresses, which are equivalent to turbulence intensities. And in wind engineering, we're more used to talking about turbulence intensities, but when you actually work with the solvers, you specify Reynolds stresses. So I'll mainly be focusing on Reynolds stresses in the fall. So there are two ways in which you can generate this inflow. And one is to do a precursor simulation that actually resolves spires and roughness elements, just like you do in the wind tunnel. Now, the solution that you would get out of this, the turbulent wind field that you would get out of this, is going to depend on how well you can resolve these roughness elements in your Elias simulation, the subgrid model that you are using, for example, the discretization schemes, etc. So you're not guaranteed that when you do an Elias simulation of this, you will get exactly what you have in the wind tunnel at the end of this domain. Synthetic turbulence generators offer you more direct control over turbulence statistics, because you actually specify into these synthetic turbulence generators, you put what your Reynolds stresses are, what you want your length scales to be. So this gives them an obvious advantage, but there is a really big challenge here. And I'll go into that further, but I first want to highlight is that, so this is the approach that we will be using because we want to avoid resolving these roughness elements. And this is also what the SimCenter has been pursuing. So they have a turbulence inflow tool available that you can find at this link, and it implements different types of turbulence generators. The one that we will be using specifically is a divergence-free turbulence inflow that was developed by Xi and Castro and then further modified in this paper to be divergence-free. And what you get here is you specify this unsteady three-dimensional velocity field at the inflow. It's a two-dimensional velocity field because you specify it at every time it becomes three-dimensional. And you see the inflow plane here, for example. And it's a function of this mean velocity profile, so your log-law, and then all of the Reynolds stress components that we have from our wind tunnel experiment, plus our integral time scales, which will determine the length scales of the turbine. So you generate this using a digital filter. You get a field that looks like this at one point in time, and then you generate an update every time. And we impose that inside of the computational domain. That makes it run through the correction step of the Piso algorithm, and it ensures that the flow field that you get out is divergence-free. And that's important because if you do not do that, you would see really big artificial pressure fluctuations, which would obviously influence your pressure statistics. Okay, so this is a standard approach that has been published. Now, the challenge that when we use these in simulations like the one that we wanted to do is that the synthetic turbulence is not a solution of the system of equations that we're solving. So what happens is we put something in at our inflow generation plane, and I'm looking at turbulence kinetic energy here. So the magnitude of the turbulent fluctuations. And as you move downstream, you see that we lose a lot of that turbulent content. And by the time we get to the building, the intensity of our turbulence is much less than what we actually intended to be, or than what it is in the Windtunnel. And we've done simulations like this. And what you see is that you're really under predicting the pressure fluctuations on the building. Okay, so we need a solution for this, right? One way would be to actually start resolving all of these roughness elements. Again, that would help, but it would really increase the cost of the simulations by a lot. And we wouldn't still be guaranteed that we get exactly the conditions that we want at the building location. So instead, what we, and this, I'll show you this first because this actually quantifies this decay. So what you see here in the gray line is the value that we want to achieve, the mean value from the experiment. And this is that span-wise variation that they measured in the Windtunnel. And you see that what we obtain at the building location is really a significant reduction compared to these values at that point. So how we decided to try and solve this is by doing an optimization. So we put into our digital inlet generator the Reynolds stresses and the length scales. We run the actual Elias, and we get, without the building, but at the location where we want to put the building in our future simulation, we extract the statistics. And we get these statistics, Reynolds stresses and turbulent length scales, and we compare them to the experimental value. If that is less than a certain allowable error, we say, okay, we found our inflow conditions and we can go run our simulations. If it's not, then we do a gradient-based optimization until we actually find the inflow conditions that will give us what we want at the building. So in order to select the design variables, because we have 3 Reynolds stresses and 3 length scales here, and varying all of these might make the optimization very expensive. We first did a sensitivity analysis. And what we did is we multiplied each of our input values by 2, and then we looked at what effect that had on the turbulence content in the simulations. So on the left here, you see the mean velocity profile. The baseline simulation is a black dotted line, and then these are all the simulations where we multiplied this specific component by 2. And here you see that they all overlap, and that is really because we use that Wall function. So that Wall function is essential in ensuring that you sustain your mean profile in all cases. What you see on the right here is how these different components at the inlet affect the turbulence at the building location. And you see here that the green and the orange line actually show the biggest increase in turbulence kinetic energy. So that means that our vertical and our span-wise stresses are actually the ones that will have the biggest effect on the turbulence kinetic energy at the building location. So we're going to use these as our design variables in our optimization. And because these are profiles that vary with height, we decided to parameterize these using Bézier curves. And that gives us control points at different heights that we can then change to get our optimal inflow condition. Okay, so just to summarize, our decision variables are these Bézier points for the span-wise and the vertical Reynolds stresses and time scales as well. And then our cost function is the least square difference between the goal function at the building site and the measurements. And we treat the Reynolds stresses and the integral time scales independently to make the optimization more affordable. This is the result of this optimization. So what you see on the left here is the inflow generation plane. So this is what we specify at the inflow. What you see on the right is what we get at the building location. So here I'm showing these Reynolds stresses that are design variables, and here I'm showing mean velocity, turbulence kinetic energy, and then the time scale, which are the quantities that we're mainly interested in matching. So in step 0, our Bézier curve is somewhat representative of the Windtunnel experiment itself. And we see that we have this decay, right? So our values of turbulence kinetic energy are too low. We're doing already pretty good on the time scale. In step 1, these values are more or less multiplied by 2. And we see that we already get a much better match to our Windtunnel data. Then we did one additional step in the optimization, which improved the comparison a little bit. So what we do now is we take these orange profiles, right, for our Reynolds stresses, and we can go and use these for our simulations with it. Okay, so to wrap up on this section on the inflow simulations, using a rough wall function is very important to support maintaining your mean velocity profile. And by adjusting your Reynolds stresses and length scales at the inflow, you can actually ensure that you achieve the desired turbulence statistics at your building location. The interesting thing is that this inflow generator with optimization will also support a systematic sensitivity analysis, because we can now go and vary our inflow parameters to get different targets, turbulence intensities at our building location, and check the sensitivity of our solution to this. So that's what we'll discuss next. Okay, so this section focuses on the simulations with the actual building and then prediction of mean, root mean square, peak, and design pressure coefficients. We have a paper under review here. We just got back the first review comments, and we should hopefully have this published in just a couple of weeks. So let's look again first at the setup of this simulation. Okay, so now we're looking at our bigger computational domain here. It's 20 meters long, it's 4 meters high, and it's 5 meters wide. We have 7.5 million cells, and we checked grid sensitivity by looking at the simulation with a coarser mesh. That simulation showed a very limited influence on the mean pressure coefficient and also on the root mean square. But when you look at a turbulence spectrum, like I sketched in the beginning of the simulation, you do see that the fine mesh is better able at resolving the turbulence into that inertial subrange. So that's why we went ahead and used the finer mesh for our simulations. The wall resolution at the ground is the same as in our inflow calibration study. And then the resolution on the building is slightly higher. We have a Y plus of 100 here. So we're still not doing a wall resolved simulation, and we'll still need a wall model on the building. So we again use the simplest subgrid model available for now. And then our boundary conditions are very similar to what we did in the inflow calibration. So on the side boundaries, you have periodic boundary conditions to ensure that we're not damping the turbulence. We have no slip on top. At the inflow, we do our digital filter with the optimization. And then on the ground, we use the same rough wall function that I discussed before, while on the building wall, we use a standard smooth wall function because the Windtunnel model is also smooth. In terms of the solver settings, so we use the same solver and schemes. We need a smaller time step now because we do have a higher resolution mesh right on the building that requires that higher time step. Our burn-in period is about 10 seconds and statistical averaging is about 60 seconds. Ideally, this would be larger, but you can see below here why we ended up stopping the simulations at 60 seconds. These take about 80,000 CPU hours on 64 processors, and that is about 7 weeks of calculation time on Stampede. So you could use more processors and reduce this physical time, but because of the scaling and OpenFOAM and the fact that our mesh is not that large, we would actually be increasing the total CPU hours here because the scaling wouldn't be ideal. So let's look at how we want to check that sensitivity to the inflow boundary condition. Okay. So in the very beginning, I showed you that span-wise variation that you have in the Windtunnel when they do the measurements of the different profiles. And you can see here in gray that variation is shown. So we have it for the mean velocity, for the turbulence kinetic energy, and for the stream-wide time scale. And what we are going to do in our inflow generator, which is this function of the mean velocity that depends on the roughness height, and then the turbulent components that are a function of turbulence kinetic energy and the time scale, is that we're going to vary these three parameters to get profiles that somewhat represent this range that we have seen in the Windtunnel experiment. And we have done the inflow optimization to get these different profiles. So we'll look at simulations with these 3 different mean velocity profiles, with something that represent the minimum, the mean, and the maximum turbulence kinetic energy, and this minimum, mean, and maximum time scale. And then we look at all combinations of this. So we actually performed 27 of these Elias simulations that take 7 weeks. So this was quite a big computational effort. Let's first look at the distribution of the mean pressure coefficient. So again, we look at all of the pressure taps on the building. This is the experimental data, and then this is the large-eddy simulation. So you immediately see that qualitatively, this prediction of the mean pressure coefficient from the Elias is quite good. When we look at the root mean square pressure coefficient, we see the same thing. Qualitatively, we're really catching this, this high region of the root mean square pressure coefficient that we see in the experiment. And it's especially interesting near the top corner here, you see the smaller region of high RMS pressure coefficients that the Elias does also capture. So to compare a little more quantitatively, you can look at profiles, and we'll be focusing on one of the rows of taps here. So this is the streamwise direction that you see here, and then you have the mean pressure coefficient in the plot on the left and the root mean square in the plot on the right. And we're not only showing the result for the baseline Elias, which is the one with the mean values for these inflow conditions, but we're also showing the sensitivity to the variability in the inflow. And that's this gray area that you see here. So we see that the inflow uncertainty does not really affect our mean pressure coefficient prediction that much, but it really has a significant effect on the prediction of the root mean square pressure coefficient. So representing any uncertainty in this respect in your simulations is key when you do this type of validation studies. When you do this type of sensitivity analysis, you can also try to do some more analysis to understand better which of these uncertain parameters is really most important for different quantities of interest. And that's what we try to do here. So we look at the main effect of each of these inflow parameters on the mean and on the root mean square pressure coefficient. And what we did is for each of the uncertain parameters, we averaged all the simulations with the minimum, the mean, and the maximum values. And then we look at the profiles that result from that. And that can show you some clear trends. So when we do this for the mean pressure coefficient, we have seen that the main effect on the mean pressure coefficient is due to the roughness length. So it's really the mean velocity profile and the shear in that velocity profile, so how large the gradient is, that is going to affect the mean pressure. If you look at the root mean square pressure coefficient, we see that the main effects are because of the turbulence kinetic energy and also because of the integral times. So the more turbulence kinetic energy you have in your atmospheric boundary layer, in your wind field, the higher your root mean square pressure coefficient will be. The larger the time scales, the higher they will be. This one needs to be interpreted with a little bit of care, and we discussed that in more detail in the paper, because it wasn't possible to only vary the time scale and keep the turbulence kinetic energy constant. So when we move to these larger time scales, we also see an increase in turbulence kinetic energy. So this effect is a combined effect of what happens to the time scale and what happens to turbulence kinetic energy. Okay, so the turbulence statistics are really important when you are looking at these pressure fluctuations. Then looking at the peak pressure coefficient next. So here we look at these local peak pressures at each of the taps. And what we plot here is actually the most negative peak that we found at each pressure tap location in the 27 simulations. And when you do that, you see that we can get as negative peak values as what you see in the Windtunnel. When we look at profiles, and so we look at the same row of taps here, and the dots are the baseline large eddy simulation, while this is the sensitivity bound. And this is the result from the experiment in Milan. We see that the baseline always has peak pressure coefficients that are slightly less negative than the experiment. And that is something that you would actually expect, because we are only looking at resolved turbulence here. We didn't try to incorporate subgrid fluctuations into this analysis. it is something that we could probably try to do, and that would decrease these peak pressure coefficients a little bit as well. Now, the question is from a design point of view, whether that is something really valuable, because we're interested in these more averaged values over panels, right? And when we look at that, so when we look at a time series of a pressure coefficient averaged over a panel near the top corner, and we did this for all of these different panel sizes, and then we get a peak estimate from that, we see that the sensitivity bounds from the LES actually fully encompass the data that was obtained in the Windtunnel. Okay, so we are capable of well predicting these design pressures on glazed panels of different sizes. Then to finish the section on the LES here, I want to quickly talk a little bit about subgrid models. So as I mentioned, we use the most simple subgrid models in these simulations, which is the Smagorinsky model on the left here. And then we also wanted to look at what happens when you use dynamic models. So we ran simulations with both a dynamic K and a dynamic Lagrangian model. And what you see here in these instantaneous velocity contours is something that we know, right? Which is that a standard Smagorinsky model is quite dissipative. So the smallest turbulence scales will be dissipated and you won't really resolve them in the flow. These dynamic models are much better capable of doing that. What does that mean when we look at the mean pressure coefficient? So here you have the experimental data, you have the simple Smagorinsky model and then the two dynamic models. And we see that these models actually do better at predicting these negative pressures in the suction, in the separation region of the flow. And you see the same here in the profile, right? So you really get that decrease in the pressure coefficient. So this is a sign that dynamic models might really have some benefit in predicting what happens in these separation regions more accurately. If we look at the root mean square CP, so this is again the experimental data. This is our result with the Smagorinsky model, and then this is a dynamic K and a dynamic Lagrangian. You also see that you have these higher root mean square values in the separation region. There is, however, an artifact that we see when we use these dynamic models, which is that we get very high root mean squares just downstream of the corner. And that is also reflected when we look at peak pressure coefficients. So these are the peak pressure coefficients on this row of tabs. This is what we had with our Smagorinsky model. And then this is what we obtained with the dynamic model. And we again see these artifacts here, right? So in my opinion, dynamic subgrid models are preferable because they do resolve turbulence better. But I do think that we need further investigation to look into what's happening here at these corners before recommending using these models for design purposes, for example. Okay, so in conclusion on the LES simulations, so if you design your LES carefully, you can reproduce pressure coefficient statistics with good accuracy. The root mean square and the peak pressure coefficients are highly sensitive to the atmospheric boundary layer statistics that you have at the building location in your simulation. And that is the same thing in the wind tunnel, right? It is often said that this is the reason why you would get different results in different wind tunnels, because these statistics do not match exactly. Dynamic subgrid models are preferable, but we need to look more into the behavior near the upstream corner for the models that we've tested so far, at least. And then the computational cost remains a limiting factor, right? Especially if you want to use these simulations for design. Important takeaways for validation studies. Experimental data sets that are used for validation should really report detailed atmospheric boundary layer measurements at the building location, including uncertainty intervals. And then on the simulation side, we should really do an effort of accounting for this uncertainty when we compare results. Even if in the wind tunnel they can characterize the boundary very accurately and the uncertainty is negligible, it's unlikely that your LES will match it exactly, right? So you might still want to check sensitivity because of these discrepancies that we will see. And since I have been a little slow, I'm going to skip the section on runs modeling, and I'm just going to end by giving you some ideas on moving forward. So we have been looking at a further investigation of subgrid models, and initial results with the Freeman model seem promising. So we're looking more into that. It's also very important to start thinking about different wind directions. This 0-degree case that I've presented here today is actually a very special case due to symmetry. And we've come to realize that as we look at more and more wind angles. And we should acknowledge that this exact 0-degree case is probably not going to occur that often in reality. Right? Speeding up the computations is something that, yeah, we're really looking into as well. There are methods that support larger time steps, which can really help a lot in speeding up the simulations, particularly by using multi-grid techniques. We've also been looking at using a weakly compressible solver that doesn't require solving a Poisson equation. And that has really shown us very, very good speed ups. I'm talking going from 7 weeks to 2 weeks and maybe even less, like talking on an order of days instead of weeks. And then the last thing that I want to highlight is that I think multi-fidelity modeling is something that we should really look into more, because that could really help to decrease the cost for engineering design. If we think about engineering design, we need to look at all wind directions, and usually in a wind tunnel that is done with a 10-degree resolution. So that would mean that you would have to solve 36 of these Elias simulations, maybe accounting for uncertainty in each of these simulations. So instead, if we could, for example, run an Elias for every 30 or 45 degrees, and then supplement that with information from Reynolds average Navier-Stokes simulations in between, we could still get accurate predictions. And the plot I show here is just as an indication of what we're working on. This was done with machine learning. For a 40-degree case, if you would just run an LES, you would get this. If you just run a run simulation, you would get this. And these are root mean square pressure coefficients. While a multi-fidelity simulation that didn't use the LES at 40 degrees, but used an LES at, I think, 30 and 50 degrees, actually can get to something that is more accurate. And then lastly, something that I think will be important, given that we see this very high sensitivity to turbulence statistics in the boundary layer, is to think about what are these turbulence statistics in real extreme wind events like hurricanes and tornadoes, because they might be quite different from what we have assumed them to be in the past. And then validation with full-scale measurements, but that is that is reaching quite far, because doing this type of measurements at full scale is quite a challenge. So that was all I had, and I'll be happy to take any questions from here. Thank you for listening.
Thank you so much, Catherine. That was extremely informative and detailed talk. It's incredible how many steps there were for this validation. We do have some questions now, if you're willing to answer some of the audience's questions.
Yes, of course.
The first one, first, thanks you for the informative talk. And they note that the region of RMS pressure and peak pressure do not overlap. I can't point to a specific slide for this, but they're asking if there's any reason for that.
Yeah, because the peak pressure is also influenced by the mean pressure. So let me try and guess more or less what slide number we would be looking at. Okay, so for the mean, you see that you get the most negative pressures inside of this separation region. Okay? For the root mean square, you get them more in the reattachment region, but the peak is not only determined by the turbulent fluctuations, it's also determined by the mean. And that is why for the peak, you will actually see these values moving upstream a little bit. So they are in that area where the mean is already very negative. And then the turbulence makes the largest peaks occur there. I hope that answers that question.
I hope so too.
It's a really good one though, because every time I look at these, I remind myself that that is what it is. So.
All right. For the LES and wind tunnel comparison, you selected a particular row of taps to do the comparison. And what was the basis for selecting that row and not others?
We've done this on different rows. And yeah, when we presented the data, we tried to pick a row that was most representative of what happens over most of the building. In our paper, we also pick a row of taps on the lower tiles here. So we have an additional row of taps there. And these are really quite representative for what happens elsewhere, except for what happens at the real top corner here. But these phenomena are so localized that for design, they're not necessarily that interesting to focus on.
Okay. What was the value of the Karinski constant that you used in the model?
The standard value, which right now I would have to look it up, but we kept like the most standard setting that you could do.
And was there any damping included?
Yeah, near the wall on the building, I'm pretty sure we do that because we are using that wall function here.
Okay. And then moving on to the computational cost, it's incredible how long these simulations take from my standpoint. And so someone's asking whether you can estimate the runtime in CPU hours for a local machine or for runtime on Stampede.
Yeah, so that was what I mentioned, I think, in the setup. So we have 80,000 CPU hours on 64 processors on Stampede 2. Yeah. And that corresponds to about 7 weeks. The key to me in trying to speed these up will be trying to use bigger time steps. We have had really successful results using a different code than OpenFOAM. I think looking into how this could translate into getting speed up in OpenFOAM as well, is something that we should really focus on. We really just picked like the methods that we thought would give us good results. And I think from there, we want to go and look at how we can speed up these simulations without compromising on the accuracy. Yeah, I hope that answers the question.
Yeah, if it was needed to speed up the computational efficiency, are there things that you could relax, and would you be able to quantify the error in that case, or would you not be comfortable with sacrificing, say, accuracy for the sake of speed?
It really depends what you want to do with this, right? And what we wanted to do here was really show that Elias can do this. And it's something that is not generally accepted yet. And Elias can do it, but like the way we did it, it comes at a high computational cost. Whenever you start to relax something, you need to check on it, right? And I think that it's so important. That's why it's so important that we do more validation studies and that we start to understand better what is it that we can relax and what not. What we have seen is that using different time stepping methods and a multi-grid solver like helped us tremendously to increase the time step. And if you can just increase your time step by a factor of 2, you will be reducing your computational time by a factor of 2, right? So we're going from 7 to 3.5 weeks. So that is really one of the first things to look at. The other thing that we have seen, but that is not something that you could do with OpenFOAM, is that when we use a weakly compressible solver, that doesn't have to solve the Poisson equation, which is the most difficult thing often to do in these simulations. You solve the Helmholtz equation instead there. That we get an additional speed up. And we see that we could get results similar to OpenFOAM in a matter of days instead of weeks. So there are really tools out there to do it. They're not all implemented in OpenFOAM, but I think trying to understand, which steps we can take to speed it up with tools like OpenFOAM is something to really look into. But we're always gonna have to check,
Great. Another question is, if you would comment on what would you change, or what would change in your analysis if you're interested in determining forces on the building, for example, the shear forces or moments at the base, which would be similar to data from a force balance wind tunnel test. What might change in your analyses?
My first question, I guess, would be are you just looking at mean forces, or do you want peak forces as well? If you just want means and even root mean squares, you can often make the simulations coarser without really affecting those results. And yeah, when you're looking at forces, you're always looking at integrated values, right? So getting these really localized peaks that accurately becomes a little bit less important, because those will average out when you're starting to look at forces. So I would say you could go coarser, which would then allow you to also increase the time step a little bit. So if I was just interested in forces, I would probably have started with something that was a little bit coarser and checked whether that would work. Yeah, that would be the main thing. I think overall, using dynamic models is probably also a thing that moving forward I would prefer doing over the Smagorinsky, but then when you do it, you start to see these little artifacts that could get you into trouble. So it's another thing to check. I mean, there are a lot of open questions in these simulations, admitted. But yeah, if you're just interested in forces, I think you can go coarser. That is the bottom line.
Great. And I think we'll have time for just one last question. We're up against the end of our hour. And this question starts with a comment, which is, thanks for the great talk. What is your vision for computational fluid dynamics for determining design wind loading versus wind tunnel testing?
Well, so I hope that with this, we're starting to convince people that Elias can do it, right? So now we need to speed up these simulations, and so that it actually becomes something that is feasible in a design procedure. I don't think we need to, I mean, the wind tunnel works quite well, right? So there's no need to really replace it. But I do think that in some cases now, we're designing buildings using just building codes and standards, which cannot account for things like interference effects. And their simulations could actually, if we can do them fast enough, provide something that is more accurate and gives more insight without necessarily going to the wind tunnel, which is really only done for essential projects these days, right? So I would see it as an intermediate solution to be able to do more detailed analysis on more buildings than what we're doing today. And I mean, if I'm honest, I think on the long run, we can replace the wind tunnel. I'm not saying we have to do it because these simulations are expensive and they'll also, I mean, they cost computational resources, and it's gonna be a matter of which one can be more economical maybe in the end. And yeah, use each one for what it's best for too. Some things in the wind tunnel are very easy, right? If you want to test different wind directions, you turn your turntable and you have a new measurement. In the CFD, you need to remesh and you need to run another extremely expensive simulation. So figuring out like what is best fit for which purpose, I think is something that we should try to focus.
Okay, thank you for those answers. We're at the conclusion of today's webinar. On behalf of the attendees, thank you, Professor Gourley, for this informative talk. We had more questions than we had time for, so we'll have to invite you back for another presentation and more time for questions. To the attendees, thank you for your questions, for participating in this webinar. Please check the SimCenter's website at simcenter.designsafe-ci.org. Check your inbox for emails from announce@designsafe with registration links for additional upcoming webinars. And thank you very much for attending today's webinar.